Okay, for this lecture, we are going to learn about chemical reaction stoichiometry. Stoichiometry equation imposes constraints on the relative amount of reactants and product in the input and output streams. So, uh, it is a theory of the proportion in which chemical species combine with one another. So, generally, what we need to have is a chemical reaction equation. So, now and then we will know um, what would be the stoichiometric equation for that equation. Okay, so let's proceed to the next slide where we have this reaction 2SO2 plus O2, and then the product is 2SO3, and then so on. Okay, so the stoichiometric ratio is the ratio of the stoichiometric coefficient in the balanced reaction equation. That means we need to ensure that this equation or reaction is balanced first before we can use this stoichiometric ratio concept. So if we have 2 mole SO2 generated, this is generated or produced, right? So we will have 1 mole of O2 consumed. So this is reacted or consumed. Okay. Same goes to here. If you have 2 pound moles SO2 consumed here, consumed because it is reacted, we can make a ratio to 2 pound moles of SO2 generated. So we can use generator produce for the one that is produced here, and then for the one that's reacted or consumed, we can use that term. Okay, in other words, for SO2 or O2, we use the term reacted or consumed. For SO3, we use generated or produced. Let's say we have 1600 kg per hour, okay, of SO3 is to produce. So the amount of O2 required is, bear in mind, we need to convert this to kilomole first because we are using stoichiometric ratio. Stoichiometric ratio is based on the ratio between the number of mole between reactants or products. Okay, so what we need to do is we change it to kilomole by dividing with molecular weight of SO3, and then we can use the ratio where in this case we need to find the oxygen mole flow rate. So if we go back to the equation, okay, here we have O2 uh, consumed, right? And then SO3 generated here. So we have the value of SO3 generated. So we use SO3 generated term here, and then we need to cancel SO3 generated. So what we need to do is, since we have changed the unit here, so here will become, it will become kilomole here, right? Kilomole SO3. Okay, so that means we can cancel this one with this one, and then we take 1600 divide with 80, then we get 20 divide with 2, we get 10. So the unit remain kilomole O2 consumed per hour. That's we need to convert back the unit from kilomole O2 to kilogram O2 per hour. So what we need to do is times with MR, we will get 320 kilogram O2 per hour. Stoichiometric proportion has the same concept with what we have learned previously, where we need to look at the formula, the reaction, okay, and then from this chemical reaction, we know that 2 moles of SO2 reacted for every mole of O2. So the proportion is 2 to 1. NSO2 to NO2, SO2 to O2 is 2 to 1. Okay, present in the feed to the reactor. For limiting an excess reactant, fractional conversion, and extent operation, we have one formula that we can use to find the fractional excess of A, where Na feed minus Na stoichiometry divide with Na stoichiometry. So this will be the formula to find fractional excess. But what is the meaning of fractional excess? Fractional excess is the ratio of the excess to the stoichiometric requirement. So that, in other words, we need to refer to stoichiometric ratio. Instead, we have the hydrogenation of acetylene to form ethane, where we have C2H2 plus H2H2, and then the product is C2H6. Suppose 20 kilomole per hour of acetylene. So we have 20 kilomole per hour of acetylene and 50 kilomole per hour of hydrogen. Here we have 50 kilomole per hour of hydrogen fed to a reactor. The stoichiometric ratio of hydrogen to acetylene is 2 to 1. We have hydrogen to acetylene is 2 to 1, right? So this is the stoichiometric ratio from the equation, from the chemical reaction. However, the ratio of hydrogen to acetylene in the feed is 2.5 to 1. Where do we get this? We have 50 here, divide with 20, we get 50 divided with 20 is 2.5 to 1, right? That's why we get this ratio. Then what is the limiting reactant? Of that question, we need to use this fractional excess formula where we have feed minus stoichiometry, right? So stoichiometry for H2 in this case is 20, 20 times with 2, because for 1 mole of C2H2 it requires 2 mole of H2 to react. That means if we have 20 kilomole per hour C2H2 means in this case we need to have 40 kilomole per hour of H2. That's why in this equation we take the feed of hydrogen, which is 50 kilomole per hour, minus with 40, divide with 40, we get 0.25. That means we know that there is 25% excess H2 in the feed. If you go back to the question, we need to suggest what is the limiting reactant. So the limiting reactant will be acetylene, because we have excess H2 in the feed. Then we have another term, what we call as fractional conversion, or F. The formula is moles reacted over moles fed. So the fractional unreacted is 1 minus F. If this F is reacted, means unreacted is 1 minus F, because conversion is in terms of proportion, and then the maximum number of F is 1. So that's why we take 1 minus F to get the fractional unreacted. So let's say we have 100 moles of reactant are fed and 90 moles react. What are the fractional conversion and unreacted fraction? It's very easy. What we need to do is look at this formula. We have moles reacted. Here we have 90 moles, okay, reacted, and then fed is 100 moles. So we will have 0.9. That's why we got 0.9 for fractional conversion, and unreacted fraction is 1 minus 0.9. We got 0.1. Now we are in the last part of this topic, where we are going to learn about stoichiometric coefficient. So stoichiometric coefficient, in any chemical reaction, we need to put a negative sign for reactants and positive for products. Okay, if we have this reaction, then this the information given. So we have 20 kilomole of acetylene, where here we have 20 kilomole. This is the feed, right? Feed. And then 50 kilomole of hydrogen. Okay, 50 kilomole. And then 50 kilomole of ethane are charged into batch reactor. Means initially we also have C2H6 in the batch reactor. After some time, 30 kilomole of hydrogen has reacted. Means here 30 kilomole of hydrogen has reacted. How much each species will be present in the reactor at the moment? Bear in mind that we have learned that negative sign for reactants for the stoichiometric coefficient means here, if we have 1 mole of C2H2, means we need to do change. Okay, we use symbol change here. So we have minus epsilon. Here we have minus 2 epsilon, because got 2 mole here. And then we plus with epsilon, because we have, this is the product, and then we have 1 mole. So in other words, we have this change or a stoichiometric coefficient for this particular process. then we have been told that 30 kilomole of hydrogen has reacted, means here minus 2 epsilon is equal to 30 kilomole. Okay, because 30 kilomole has reacted. So if you go to the next slide, okay, here means we have 30 kilomole here. We need to find the value of epsilon. So what we need to do is 2 epsilon equals 30 kilomole. Just ignore the sign of negative here, because it depends on whether it is a product or reactant. Later on we will substitute the value of epsilon into the equation. So we have epsilon equals 30 divided with 2, 15 kilomole. So here it's easy, we just take 20 minus epsilon for C2H2, and then we will have minus 15, we will get 5. Here just now we have 30, right? 2 times 15 is 30, 50 minus 30 is 20. Then last but not least, we have 50 plus 15, we will have 65. So that's why we for this is to summarize what we are doing here. Okay, so if you go to the solution, that's why we have the answer for um, number of mole leaving number of hydrogen leave number of mole of hydrogen leaving the reactor is 20 kilomole of H2, because we have calculated here just now, right? And then um, we have 5 kilomole of C2H2 here, and then 65 kilomole of C2H6 here. Okay, so you can try to do it on your own. If you have any question, you can ask me uh, anytime via WhatsApp, or you can always ask during class as well. Okay, thank you. That's all for this lecture. All the best, everyone. Assalamualaikum warahmatullahi wabarakatuh.